Hello, Lucia. How are you? I'm back. I'm back after a long time. Let's go. How's it going? Can you hear me? Yeah. Is everything working properly? Hello, Ralphie Wheezy. How's it going? Welcome. So yes, it's all seems to be working. So let's just get started then. So we're gonna be doing the bi-weekly contest. All good, just like all times. Exactly. Well, hopefully better, even better than old times. So we're gonna be doing the bi-weekly. Here's the link. Let me pin this. So this was the first contest on last Saturday. The bi-weekly. Maybe you've done it, maybe you did not, but let's go over the problems. So let's start with Q1. Here's the link. I think here my coding screen is a little small. Is the size of the font good? Looks good to me. All right. So Q1 is minimum operations to make array values equal to k. Okay, so as the title says, there's an array integer array nums and an integer k. And first they say an integer h is called valid if all values in the array that are strictly greater than h are identical. Okay. So here we get a few examples. So here we have 10, 8, 10, 8. So 9 is valid because the numbers that are strictly greater than 9 are only these two tens, which are identical, right? But 5 is not, because in that case we're going to have 8s and 10s that are greater than 5. They're different, so all right. So they define this valid thing. You're allowed to perform the following operation on nums. Select an integer h that is valid for the current values in nums, and for each index where nums of I is greater than h, we set nums of I to h. Return the minimum number of operations required to make every element in nums equal to k. If it is impossible to make all elements equal to k, return -1. And here we have an example. So maybe we can work out this example. Have you guys solved this one? What the hell is this? Okay. Yes, I participated in the contest. That's great. So we have two. So maybe So notice that when we choose an h, the only valid values for h are gonna be so if they are greater than or equal to the maximum, then they're not gonna change. It only changes numbers that are greater than h, right? So if it is greater or equal than the maximum, then it's not gonna do anything, right? So that, and so it has to be less than the maximum. But if it's less than, so for example here we have, let's sort this, right? Because the order doesn't really matter, right? So we have these numbers, right? So if the number is less than 4, if this h is less than 4, then it's going to include, in the numbers that are greater than it, it will include a 4 and a 5, right? At least a 4 and a 5, and they are different, so it cannot be less than this, right? So it has to be between these two values. And notice that what's gonna do, it's gonna reduce all the values that have the elements that have the maximum value, right? They're gonna reduce it. But if we don't reduce it to the next smaller value, then we're not gonna make any progress, right? Because then after that we're gonna have to do another operation that is also going to modify only those numbers, and we still have to reduce them, right? So I'm saying that we always want to choose as h value here the value that is less than the maximum, right? So in this case it is 4, right? So if we apply the operation with 4, that means that all the numbers that are greater than 4 are going to be turned to 4, right? So now we get this, right? And so now we apply the same logic, and so we have to choose h. It's optimal to choose h equal 2, and so we change all the values that are greater than 2 to 2, right? So now we have 2, 2, 2, and 2. And now we're done because they are all equal to k, right? K is 2 here. So it seems that, well, so notice that every time we apply the operation, we're reducing the value of the values of the elements, right? We can never increase them. So that means that if the minimum of nums is less than k, then we can't do it, right? Because, like I said, we're never gonna be able to make them equal to k. And then the numbers that are the values, the values that are equal to k, then we can ignore those, right? They are already equal to k. They're not gonna matter, right? And then the values that are greater than k, we're gonna be doing this algorithm that we just described, right? We're gonna turn all the ones that have the maximum value to the smaller value, and then all of those to the smaller value, and so on. So for all the unique values that are greater than k, we have to do exactly one operation, right? So that gives us our solution, our algorithm. So, hey Bobby, holy, so I'm back as I promised, right? So it took me a couple of days, but I'm here. So let's do it. So we can do a one-liner here. So one condition that we set, right? We said that if the minimum is less than k, then we cannot do it, right? We have to return -1. And notice that if that's not true, then we can do it, right? Because the algorithm that we described is always going to work by reducing the numbers up to k. So now what do we want? We want the number of the unique numbers that are greater than k, right? So remember that when we want, usually when you want to count unique values, you use a set, the length of a set. So one idea would be to just filter the x's that are greater than k, right? We want to ignore the values of k because those ones don't require any operation, right? And so this should work. Yes, sir, man of a word. So this is our one-liner. It works pretty fast. It's optimal, I think. Yeah, I think a little different implementation would be to do this and then subtract the set that has k, right? Because yeah, this is the difference of a set. So if it doesn't have k, it's not gonna do anything, right? So this should also do what we want, and it's a little shorter. Cool. So thumbs up. So here's my solution in case you want to check it out. So was the explanation clear? I think Chandu, I don't know if you are here, but maybe I'm gonna recommend you to watch this video if you're not here. But because I know you had trouble with this problem, so I'm wondering if my explanation made it clear. I tried to make it complete. So that is how I would investigate this problem, right? Like doing all those steps that I went over. Anyway, so let's go to Q2. This probably can be done brute force too, but this way is much shorter. Yeah. Yes, you could do. Yeah, that's a good point. You could just yeah, but I mean, you still have to have the observation that you always want to choose that h, the h that is the smaller, the next smaller value. So I don't think it makes sense to simulate it in that way, like. So yeah, and also yeah, you have the for Q2. Can you please do it not like in one-liner? I feel like some people don't use Python, easier to follow. No, so about that. So here I'm using a one-liner because I think it's pretty concise and it is clear. Sometimes people abuse like make code golf solutions to get to a one-liner. That's not what I'm trying to do. So yes, I'm trying to make the code clear. So if it is not, let me know. So I'm not going to use a one-liner probably for Q2. So yeah, so the sizes. So notice that I didn't even look at the constraints. That's not a good practice. You should always pay attention to the constraints. But here, it was clear that we had a linear solution, right? So that's the best you can do, right? You have to read the input, so that's the best you can do. Okay, so let's go to Q2. So I was surprised that this is a part 1, but there wasn't a part 2 in this contest. So maybe we should be waiting for a part 2 of this problem in some next contest, some future contest. Bob is stuck in a dungeon and must break n locks, each requiring some amount of energy to break. The required energy for each lock is stored in an array called strength, and strength of I indicates the energy needed to break the ith lock. Yeah, I think today I was for some reason I thought about, because this is talking about Bob. Yeah, this is talking about swords. So usually you have when you have a sword, you have to kill monsters. So that's why I hallucinated that this problem was about killing monsters, but it's about breaking. It's about breaking locks. Okay, to break a lock, Bob uses a sword with the following characteristics. The initial energy of the sword is 0. The initial factor by which the energy of the sword increases is 1. Well, here also, when they use the word factor, I immediately thought about multiplication. I thought that it increased like exponentially, but then I realized that it was addition. So anyways, never mind. Every time the energy of the sword increases by the current factor, so every minute it does that. To break the ith lock, the energy of the sword must reach at least strength of I. After breaking a lock, the energy of the sword resets to 0, and the factor x increases by the value k. Okay, here's another input value. Your task is to determine the minimum time in minutes required for Bob to break all n locks and escape the dungeon. Return the minimum time required for Bob to break all the n locks. Okay. Well, here's something. Whenever you see this, so whenever you see such a small number, so the number is 8, right? So that's a red flag in a problem. Why would they make the size 8 if it wasn't because you had to do something very inefficient, some brute force algorithm? Even k is small. This is kind of, I don't know why k is small. Why is k small? Yeah, this I don't know, it could be bigger, but n is super small, right? And when if you're experienced in competitive programming, so 8, so there are sizes, right? There are sizes that suggest some kind of algorithm order of complexity, and this kind of number suggests some factorial, right? Because factorials grow very fast, and even when they get to, I think, 13, they're already too big for doing algorithms. But 8 factorial is like 40k, so that's pretty small. But I'm getting ahead of myself, I guess. But so now, with that in mind, the fact that something about order, I didn't see the 80 initially and fell for the trap. Started by trying something greedy. Yeah. Yeah, so yeah, maybe. So they were generous in the sense that example 1 shows you that the order, well, I guess the most intuitive thing would be to break the locks from smaller strengths to larger strength, because since the what is it, the factor, so k, the factor x increases by so the factor is bigger for, of course you're gonna kill, well, you're gonna break the locks in some order, right? It doesn't make sense to switch from, so to hit a lock before and switch to another lock before breaking that one. No, you're gonna choose one, you're gonna hit it until you break it, and then you move on to another one, and so on, right? So you have to decide in which order you're gonna do it. And so maybe intuitively it would seem like you want the weakest locks first when you have the less, the factor is the smallest, right? But turns out that example 1 already tells you that that's not right. So maybe we can work that out. So what is this? Is 3 for 1 and k is 1. And k is 1, right? So let's say, so these are the strengths, right? And so let's say that we sort them. And so we're gonna be breaking them in this order, right? So initially, so I'm a little bit confused about this. So you here, yeah, so for the first one you have each time you hit it, is it, how do they explain this? Okay, so the energy of the sword gets incremented by this number x, right? Which is initially 1. Right? So we have this x, which is 1, right? And we have to get an energy greater than or equal to 1, right? So it takes us 1 1 minute, right? For this one. Now we move on to this one, and now our x is we add this one, so our x is 2, right? So how many times do we have to increase the energy? Well, 2 times, right? We get to 4, and then we break it, right? So we need 2 times, and then we increment this as well, and now it also takes 2 times to break this lock, right? Because 3 is not enough. We need 6 to get. So our answer is 5, but that's not the answer given here, right? It's the answer is 4. So maybe if we did it in this order, then again we have x equals 1, so we need 3 minutes to break the first one, and then this increases to 2, and so now we need 2 to break the fourth one. Wait, no, is that the order they're doing? Break third lock. No, they're doing 1, then 2. Okay, so in reverse order, right? So they're doing 1, 4, and 3. Okay, so here let's correct this. So the first one takes 1, okay, and now the second one takes 2, right? But now the third one is gonna take only 1, right? So that's why the answer is 4, right? And this proves that the sorted order is not optimal, right? So I don't know if there's if someone knows what the optimal order, if there is a greedy algorithm. Probably not, but if we, again, now that we know that we need to know what the order should be. Okay, let's try them all. So in Python, we have a very convenient function. I tried a couple in the contest, none worked. Lol. Yeah. So let's just try them all, right? There are so let's check. There are 8 factorial permutations of 8 elements, which is 40k, around 40k, right? So that's very small for a program. Oh, wait. So let's have a permutation of strings. Let's rename this to S because that's hard to type. Okay, so we have our, well, let's call this S. Okay, so this is our strengths, right? And we're gonna try to find a minimum, right? So let's initialize this with infinity, and now we want to go over the strengths. And so remember that we need to have well, x is the factor as they call it, which is initially 1. So this is okay, so these are the strengths. So we add an S for plural, and this is the strengths of the current one. And so how many times, and we're gonna count the current time, right? The time of this order, right? So how much time do we need to break? Well, we want x to exceed, so s, we have to divide it by x, the factor, and we take the ceiling, right? Because that's how many times we need to get to s or more. And then when you break the log, the factor increases by k, right? And now we want the minimum. The minimum time, right? And so this should be it. List object. Oh, what I wrote range. Permutations. And this is it, right? Is this clear, Bobby, in terms of the code? Can you explain the formula? You mean this formula here? Well, this is how many times, so it is a division, right? So if you have 11, so your strength is 11, and your x, your factor, is 2. So how many times that do you need to add 2 to get to 11 or more? Well, if you add it 5 times, right? So 11 divided by 2, rounded, so it's 5.5, right? So so with 5, you're gonna be short. You're gonna be 1 short. So you need to round up. That's why we take the seal, which is 6, right? So this is the idea. Because so it's simple, right? So every time, how did you become good at LeetCode? I have solved 300 plus questions, but I still struggle a lot. Well, with a lot of practice, but yeah, it takes time, right? So keep at it. I have a lot more than 300 problems solved, right? So but hopefully my streams can help you out, and you can also join my community in Discord and ask questions there, and I can help you out to get better. So the answer of how to get good is to solve problems, the short answer, but there's a lot more than that, right? So if you want more details, I suggest you to join my community. All right, so okay, so the code is clear. That's good. So notice that, yes, this is what Lucia is saying. So I think Bobby is gonna complain if we do this. Yeah, the Discord link, I think it's in my my profile in Twitch. Let me know if you find it. So yeah, so there's a so usually you wanna, so here we're doing floating point division, right? So we're using a float, and then we're doing the seal, and usually you want to avoid floating point numbers because you could have there are edge cases where you can have precision errors. So this kind of division can be done by like this with integer division, and it's the same idea. Yeah, here, well, that's why I use seal, because I thought it would be more intuitive for people who don't know how to do this. So and so now we can try. Okay, so this is more advanced. Okay, so bear with me, but there is another way of solving this problem, which is with DP. That it's more efficient. It would allow us to, so with this kind of solution, we can only solve, so we could solve bigger instances. So if you look at this, like 10 factorial is still pretty small, right? It's 3 million, right? I think at 13, or yeah, even 12 is already half a billion, right? So even 12 is already too big, right? So if we had a variant of this problem where the n could be bigger, it could be 12, it would be too slow, right? So, but there's another, with this DP solution, we could solve instances of up to 20, for example, which would be which would take like maybe more than the like an incredible amount of time if we did it this way, right? This is crazy, a crazy number, right? So time complexity for permutation solution is, yes, it's n factorial times n. Which is pretty bad for the time complexity, but it's good enough for a contest, for these constraints. So that's what you want in a contest. You want the simplest thing that works, that is good enough. So I'm wondering if I should implement the DP solution. What do you think? I'm not gonna be able to explain all the details, I think, but I can show you how it looks like. What it looks like. Well, no, I'm gonna leave it. Okay, so let's leave it for another moment. I think I share that in my Discord, if you're interested. So let's leave that one for another time. So wait, why can't I see my submission? Okay. Okay, so here I'm sharing the link to the solution, and let's move on to the next problem. All right, so Q3, it's called digit operations to make two integers equal. So we're given two integers and an m that consists of the same number of digits. Okay, pay attention to that. You can perform the following operations any number of times. Choose any digit from n that is not 9 and increase it by 1. Choose any digit from n that is not 0 and decrease it by 1. Oh, thanks for the link to the problem. I forgot. So the integer n must not be a prime number at any point, including its original value and after each operation. The cost of a transformation is the sum of all values that n takes throughout the operations performed. Okay, this is interesting because, well, that return the minimum cost to transform n to m. If it is impossible, return minus 1, a prime number. Well, okay, we know what a prime number is, right? It's a number greater than 1 with only two factors, 1 and itself. Okay, so, and the numbers are less than 10 to the 4th. They have the same number of digits. So yeah, let's pay attention to this, that because the cost of the transformation is not the number of transformations, it's the sum of all the values that n takes. So that is important. And there is one thing that is not clarified in the description, and that I assumed that it was allowed, but it turned out, so I got a wrong answer in the contest because it wasn't allowed, but it's not specified in the description, which is that you cannot decrease the leading digit. You cannot decrease it and make it 0, right? All the numbers have to have the same number of digits. And that changes the answer. It turns out that you can get better, so lower costs by doing that. So it does make sense. They should have clarified that that's not possible. Okay, but okay. So now we know, after I got the wrong answer and I was confused. Okay, so this problem is pretty standard, right? We're trying, yeah, agreed. So we're trying to find, so we can think about the numbers as nodes and the transitions, right? The transitions are edges, right? We can get from a number to another number, right? That means that there is an edge. So, and the numbers that we're given, right, are n and m, right? So those are nodes, and the edges have a weight, right, which is this cost, which is the value, right? And so this is essentially they're asking to find the shortest path from n to m, right, in a weighted graph. So that's a classic problem. It's the single source shortest path problem. And the way to solve it, the algorithm, is called Dijkstra's algorithm. When the weights are not negative, you can use Dijkstra's algorithm to solve that problem pretty efficiently. So this is what we should do. That is pretty much you ideally you want to have studied Dijkstra's algorithm and you want to know how to implement it quickly, right? So we are going to, well, first of all, we have this condition of the prime numbers, right? We can't do the p because there are cycles, right? Yes, that is true. And so here we want to know whether a number is prime, right? We want to know that in O of 1. We want to know that very quickly, right? So it's not gonna change the order of complexity of the Dijkstra's algorithm. So how do we do that? Well, we can use a sieve. I think I explained that before. So the numbers go up to 10 to the 4, right? So we want to ask for, we want to be able to ask for any number less than m, whether it is prime or not, right? So we're going to create a table. So remember how this works. For sieve, if we put aside the class solution, means that it's only run once, right? Yes, exactly. Yeah, good point. So I'm doing this outside of the class, so it's going to run only once for all the test cases. That's why I'm using the maximum value in the constraints, right? I'm not using the values here. So because it's going to work for all test cases, right? So here, first, in the sieve, first all the numbers, you mark them as prime at the beginning. Less for I don't think we're gonna ask for these numbers, maybe. Well, for 1, we might ask for 1, so let's make sure we mark those as non-prime, and then we go for the primes from 2 to m, and if it is prime, then we go over the multiples from the square of the prime up to m, and the step should be p, right? Because we want the multiples of p. And then is prime of n is false, right? Because it's a multiple of a prime that is not the prime. All right, so this is it. Now we can ask whether a number is prime very quickly, right? So here, so there's a special case, right? And I think some people got tripped by this, but so if this is what it says here, right? So including its original value, right? They cannot be. So if n is prime, we return -1, right? Just to make sure. So now we're gonna do just our Dijkstra, right? We should have a template, like a way that we know how to code it. So in Dijkstra you have a heap, right, where you put the distance. So the distance so n is our initial node, and the distance to n is n, right? So this is our initially what the queue, the priority queue is going to be. And then we want to have a dictionary of the distances. The smallest distance so far. So again, we want node n to have distance n, right? And so while the queue is not empty, we pop from the queue. So we're going to have the distance to u and u, right? So we do heap pop, And remember that if the distance to u is not the same as the smallest distance so far to u, then it means that we already processed this node, right? So we ignore it. And then we check if u is equal to m to the final state, to the destination, then we return the distance to u, right? At the end, if we finished and we never reached m, then we're going to return -1. And then we're going to have a function. So we want all the adjacent nodes b, and we're going to have the adjacent nodes of u. We're going to have a function that gives us that, right? Some other people call it the neighbors or the adjacent, whatever. So so b cannot be a prime, and then the distance to b is going to be the distance to u plus b, right? And so now we check if the distance to b that we have so far, right? Which we're gonna make it infinity if we haven't seen b. If we don't have any distance yet to b. If this is greater than the distance that we found going through u, then we want to update it. And we want to push to the heap dbb. Okay. So this is our Dijkstra, right? So now we only need to know the adjacent of u. Okay. So let's get the number of digits of u. So I'm gonna do this. So there are different ways of doing this. You can do it. We can do this with strings. Good idea to abstract in a function the adjacents. Yeah, I think it's pretty. It's a pretty independent task here, right? So this is like a pure Dijkstra, except for the East Prime thing. We could even put the East Prime thing here, but I mean, it's not a big deal. So now, so the number of digits is this. So one way of doing this is to use strings, but I'd rather use numbers. I think it's faster, and I think it's not bad. So we want to go over the digits, right? So we're gonna iterate the number of digits, and we want to check the current digit that is gonna be this mod 10. If we use string, would it TLE? No. It's just sometimes so it won't TLE in this problem, but it might TLE in another problem in the future. So I'd rather, if I had two ways of doing things and I think they are equally clear, I would choose the one that is faster. Okay, so here we have d is the digit. So if d is less than 9, so we're gonna have yeah, I think we need to, because I'm gonna I'm going to be destroying the number, right? Because I'm going to be dividing by 10 in order to go over all the digits. But I want to remember the original number. And P is going to be the power of 10 corresponding to the current digit, right? So I'm going to be multiplying by 10, right? So here, if it is less than 9, then I can increment it, right? So I'm going to yield U plus P, right? So that is one option. I increment it. I increment U by the power of 10p, right? That's incremented that digit. What is yield? This is just a way of it creates a generator. It's I think it's similar to. Okay, so maybe I can use. Well, let's not use yield. Okay. We just append this to the result. Okay, so if D is greater than 0, then we want to decrement it, right? And so here we return res. But yeah, so read about yield is very convenient in Python. Well, but here there's a special case, right? Because we cannot decrement it if we are in the last. So we're going from the least significant digit to the most significant digit, right? And so this is okay, so I explained it. So this expression here, it's going to be 1 when we are at the most significant digit, right? Because of the index here. That is the last value of I in the iteration, right? And D minus 1. So when we are at the most significant digit, this is going to be 1, which means that we can only decrement if it is greater than 1, right? If it is 1 or 0, we cannot decrement it, right? But for any other digit, this is going to be 0, right? This is going to be false, right? So the number is going to be 0. And so that's going to be the expression that we had before, right? That D is greater than 0. So this is it. If I is greater than 1, yes, I mean, you could do this by saying I is equal to an D, and D is greater than 1, or I is different than this, and this greater than 0. But it is a little longer, right? Do you prefer this expression? With strings, it's a little easier because we can go from left to right rather than right to left. And why does that make it easier? No, this is right to left, right? It is from least significant. So we're doing mod 10, right? This is given the least significant digit, and then we divide by 10. So we're dividing by 10 is like shifting to the left. Okay. Okay, shall we move on to question? Is there anything else to say here? So this you might have, so the sieve thing sounds good to me. This you might want to have it in your template. So it's good to have like a library of things, of code that you reuse, that you can copy paste in a contest. And this is pretty much this doesn't change, right? I mean, there are variants, but for primes is always the same. In the case of Dijkstra, I mean, you could have a template, but usually there are things that depend on the way the graph is defined. So here we have this isPrime thing that is only makes sense in this problem. So I mean, you can have a template, but you will usually have to modify it. You won't just copy paste it. All right, so let's move on to Q4. All right. So Q4, count connected components in LCM graph. LCM means least common multiple. You are given an array of integers nums of size n and a positive integer threshold. There is a graph consisting of n nodes, with the ith node having a value of nums of I. Two nodes I and j in the graph are connected via an undirected edge if the LCM of nums of I and nums of j is less than or equal to the threshold. Return the number of connected components in the graph. Okay, well, connected component, I think we know what that is. And this is the least common multiple, as I said before. So here we have example 1. And here they draw the graph, right? So the problem here is that the number of nodes in the graph is 10 to the 5th, right? So if you were to build the graph like naively, you would have to go over all the pairs and do this, right? Do this check, the LCM, calculate. So the LCM is it's already in Python in the math, and is logarithmic in time, so it's pretty fast. So you would do that, and that will tell you whether two nodes are connected. But of course, the number of pairs of 10 to the 5th, that's quadratic, right? That's the squared. That's order of the square of that. So that would be 10 to the 10th. So that would be very slow, right? So we have to be clever. So what can we do? So let's think about this example first. So only 2 and 4 are connected here. Why is that? Because so the least common multiple of 2 and 4 is 4, right? And 4 is less than or equal to the threshold, right? With than 5, so that's why they are connected. But if you try any other, so notice that the multiple, so the least common multiple, it's gonna be a number that is greater than or equal to both numbers, right? So if a number is greater than the threshold, then the LCM with any other number is going to be greater than the threshold. And so it won't be connected with anything, right? They will be isolated nodes. So here 9 and 8 are those kind of nodes. Those nodes will always be isolated. So we could process those separately and just count them as components and just ignore them, right? So that means, that's interesting, because notice that the values are up to 10 to the 9th, right? But that's a trick, right? That's a red herring, because like we said, we can ignore all the numbers that are greater than the threshold. So actually the values that matter will be bounded by this this number, right? So so that's one thing to notice. So here, what you need to take into account is that so the LCM has to be less than or equal to the threshold, right? So that means that the LCM, so the threshold is a kind of a small number. So what if we consider each value, right? AKSR, hey, how's it going? It's trolling? What do you mean? So what was I saying? Okay, so let's say that we guess is it numbers? How do you know? I mean, I think numbers is not an X number. Is he? I know who numbers is, but is that his account in Twitch? And I am why would that be a troll? Doesn't make sense to pretend to be a beginner. How is that a troll? Anyways, let's see. So let's say that we consider the number x, right? And this is less than or equal to the threshold. Okay, so what happens? So let's say that we have two numbers, a that divides x and b that divides x. So if both numbers divide this x, then the LCM of a and b must be less than or equal to x, right? Because x is a multiple of both of them, right? And the LCM is the smallest, the least common multiple, right? So this is pretty clear. So that means that A and B, so if this is true, A and B are connected in our graph. Connected, right? Because we chose x to be less than or equal to the threshold, and we have two numbers that divide x, so their LCM has to be less than or equal to x, and therefore it is less than or equal to the threshold, which is the condition for connectedness, right? So this is very interesting, because now if we went over all the x's, right? So s in range from 1 to the threshold plus 1. Okay, this guy is spamming. How do I? How do I kick someone? Okay. So now if we consider all the x's, right, and then we can go over all the divisors of x, of each x, for the use your remote power to ban him, and divisors of x, then we know all those numbers are connected, right? So then we can use the union find data structure to connect them. So notice that if we have A, B, C, D, all that are divisors of x, right? So all their pairs, so all the pairs are connected, right? Because of what we proved here. But in the union find, we only need to connect them with one, right? So we can choose this one as the first one as the representative, right? And we connect them all to this one, and they will all be in the same connected component, right? So that is the idea. So instead of doing it this way, so there's a way So notice that we used a sieve in the previous problem. So here we can use the same idea of the sieve to go over all the divisors, right? We want to go over all the divisors of the numbers in the range from 1 to. So we can do it, instead of doing this way and going for the divisors, we can do a sieve, right? We can go, so for D in range from 1 to the threshold plus 1, and then we do like we did with the sieve, right? We go for the multiples in range, so D threshold plus 1 and D, right? This is gonna go over all the multiples of D, including D itself. And so here we can do something with that. And this is the order of this is n log n. I mean, you can believe that it is fast if you already know that sieving is fast, right? Because it's the same pattern. But so this is because of the harmonic. So maybe I can explain why this is n log n. So notice that in the first iteration, D is going to be 1, right? And so the number of divisors are going to be, so let's call, instead of using th, or let's use n, right? So the first, for d equals 1, this loop is going to go n times, right? Then for d equals 2, it's going to be n divided by 2. And for d equals 3, it's going to be n divided by 3, right? This is how many divisors of 3 are, right? And so on, until this gets to n, and so it's going to be n divided by n, right? So here we can take common factor n, and so this is going to be 1 over 2, 1 over 3, and 1 over n, right? And so, and this is what is called the harmonic sum. And you have to believe me that this is, so the sum is O of log of n. So the whole thing is n log n, right? So you can check this in Wikipedia. So I guess that's all we need. So I'm gonna be using, from my library, I'm gonna be using the, like I said, the union find. I'm gonna see if it works with so I have a version of union find that is or the DSU, which doesn't do, so it's very simple, and it doesn't do the union by rank, the optimization called union by rank. It just does path compression, and I read that is enough for competitive programming. So we're gonna try it out. So as you see, it's very simple. All right, so now let's write down. Let's write this down. So okay, so we have the disjoint sets, and this is going to have disjoint sets of n. So like I say, we go over all let's call this DH to make it easier to type. For union by size rank, the time complexity for both union and fine aberrations slog. It's more complicated than that. I mean, it's not the log. It's the inverse Ackermann function, I think. But you would have to read Wikipedia for more details. But I mean, it's fast. That's all you need to know for practical purposes. Okay, so what was I doing? So here I want the multiples, right? So I'm gonna go from D this, right? And I'm gonna save a representative for each value, which is gonna be this representative that I said. So I'm gonna for each x, I'm gonna save the first divisor that I see. I'm gonna save that one, and I'm gonna connect all the other divisors to it, right? So initially I set it to -1. And so here I want to check if the representative of m is -1. It means this is the first divisor for m, right? So we set D as the divisor. Else we want to do the union of, well, but notice that, well, we have to pay attention to this. So how did I? Yes, we're gonna use, so notice that the union find uses indices, right, for the nodes, right, from 0 to n-1, right? But here we're using numbers in this list. So we need to have an index. We need to find the index for each of the numbers, right? Which is going to give us the index in the graph, right? So for that we want to enumerate nums. And so now for each value, remember that the numbers are unique, so this makes sense, right? So for each value we have its index, and that's what we're going to use here, right? So here we want the index of the node D, right? D is and the index of the rep of M, and we want to connect them, right? And then in the end we're going to go over all the nodes, and we're going to say we're going to get the representative of that node, and we want to know how many there are, how many different there are, right? Because that's going to give us the connected components. No, I thought for union by size the TC is inverse Ackermann. It's Ackermann, I think, not Hackermann. However, if union by rank, union by size and union by rank. So no, I think it's the Ackermann is for union by rank, if I remember correctly, but Yeah, so I read this in the Corman book, the CLRS book. Definitely not. Okay, you're very sure. Okay. I got yelled at. What? Okay, let's check that out. That offline. I'm gonna check that offline, and I'm union by rank. Union by size. Time complexity. Using union by rank gives a running time. Here it says union by rank, by size or by rank. So it's not true. So are you saying that it changes if it's by size or by rank? Here it says it's the same, and this is a thing. What it's saying is that if you don't use path compression, then it is m log n. Do you agree? What is wrong here? Runtime error. Well, does this make sense? Because here, well, yeah, I don't want to go. No, I don't want to go over all the divisors. I want the divisors that are the numbers in here, right? Yes, of course. Right. So here I can use this index directly. I don't have to use enumerate. And here I can just save it as the representative. I can say the index, and so here I can use this. And so I don't need this, actually. Okay. This is called find. Okay. Cool. Accepted. So Bobby, you nice. So did you see the code is pretty simple? And I hadn't solved this one. It was educational. Great. That's the point. Yeah, notice that. So usually when you do the sieve, you go the numbers from smallest to largest. And so my intuition would be to sort this, but it's not necessary, right? Because it doesn't matter which one. So we're going over all the divisors, and it doesn't matter which one we use first, right? Which one is the representative, as we call it. So that's nice. The code is pretty short, right? Even with these joint sets. I'm confused. I will send you my union template on Discord later. All right, no worries. Well, but I mean, comments on the internet are not like the most authoritative source there is, right? So I'm not sure why you're so confident because someone said it. Okay, NCC. Yeah, I know NCC, but I don't know. Maybe he was misinterpreted, or maybe he was wrong, or maybe he's right. Anyways, let's continue with that on. Do you understand? Did you understand the solution? The idea. So this was the key, right? To think, okay, if I consider any number x that is less than or equal to the threshold, and I consider all any two divisors of x, right? Then I know they must be connected in this graph, right? Because their LCM has to be less than or equal to x, because it is the least divisor, multiple, sorry. And so then it meant that we could go over all the divisors of all the numbers in that range and connect them with the union find data structure, and that's it. It wasn't very difficult, I think, this one. So I had a bug in the contest. That's why it took me longer. So I had a very, very silly bad. It was a bug in my library code, actually. So it's good that I found it and I corrected it. Anyways, that's all I have. Do you have any questions? So I'm back, and I'm planning to start doing streams again every week. At least trying to do the contest streams, and maybe more. Let's see. Yes, contest streams. Stream during contest. Just kidding. Yeah, people. I think Larry does like records himself doing the contests and then uploads them after the contest so that people don't cheat. But I rather, so my style is more of teaching. So I'd rather think a little more about what I want to explain. But yeah, sometimes the live solving is good to get a glimpse on how people actually think about the problems, like if they think out loud while they are solving new problems. I've done streams like that before, but they're different style. Anyway, so okay, thanks a lot for watching and for your support. Join my Discord. we're growing a very good community, and I'm trying to I'm spending time there helping as much as I can. We're even doing see you at the daily chat later. Yeah, see you later. We're also doing Advent of Code every day. I also do private classes. So if you're interested, message me on private. So yeah, that's all. Thanks. See you all on Discord, and bye bye.